May I start?
Let me see. Yeah, please.
Okay. Good morning. Youngmin, Seonghyun, and I are from Nifty Chips Laboratory in Hanyang University, and we are going to present about layout generation framework, which is LAYGO2, and I will introduce the LAYGO2 and explain the key concepts to you. The presentation will proceed as follows. I'll explain what the LAYGO2 is and then keywords to you, and my slides end with the deep dive into LAYGO2. Okay, then let's figure out what the LAYGO2 actually is. LAYGO2 stands for the second version of layout with gridded objects, and originally LAYGO was developed for a template and grid-based layout generation engine for Berkeley analog generator, and LAYGO2 is the improved version of it. And the key features are following. LAYGO2 aims the automatic generation of DRCA and LVS clean layouts in various technologies. And LAYGO2 has powerful strengths on parameter-based layout generation, and it works for high-end technologies such as FinFETs or gate-all-around FETs. And also, since the LAYGO2 is based on Python, and so the designers and programmers like you guys can easily access to the LAYGO2 API. And then why do we focus on LAYGO2? Anyway, technology scaling story is far from us. This is because we are in open source area, and global EDA tools have limited access to general designers. It is too expensive. But many skillful engineers, such as SSCS and MOSAIC, are trying to democratize IC design with open source tools. LAYGO2 then can be the best solution thanks to its various interface package. For example, an integration progress of Magic into LAYGO2 took about a month. Then let's find out how LAYGO2 places instances and route wires and create pins and then extracts to output formats. The first keyword is template. According to the LAYGO2 dictionary, a template means a group of primitive devices to build a basic transistor. A basic transistor here means the structure that can be placed in a row without violating design rules of each process. Core, boundaries, and dummy devices are created in your hand and then saved to a template library. It is also recommended to use an even number of fingers since the LAYGO2 is developed for high-end technologies. And design rule of each process is different, so you need to build those primitive devices with your own hands. And also, P-cell-based template generation was updated a few days ago, and template transistors are created by placing well-designed primitive devices and routing local interconnects. And this transistor is not located in your Virtuoso library because this is treated as a virtual instance class, so it does not exist in your Virtuoso library. And LAYGO2 manages templates and grids with YAML formatted file. For example, primitive cell name of NMOS is defined like this figure. And the size, pin names, and locations are defined as the 2x2 matrix. The detailed explanation will be given by other presenters. The next is for grids. Grid means discrete and non-uniform coordinate systems that instances and pins are located. Since the routing method is different for various technologies and user groups, so users can define their own grids for their usage. And objects then can be placed based on the relative positional information by following grids. And assuring reusability is hard if you place with hard coding on physical coordinates, since the size of instances can be different across the technologies. So relative positional information can make it clear because you can place and route instances like original design even if the size changes on abstract coordinates. For example, 1,1, how do I pronounce this position? I don't know. Anyway, 1,1 in LAYGO2 on integer coordinates of specific grade then can be different position, actual physical coordinates in different technologies. The key is that users only utilize left, right, bottom, or top commands, not the actual points. LAYGO2 covers the rest of the process. And then the actual spacing on meta tracks doesn't have to be uniform, even if we use integer coordinates. There are many things to consider for layouts: local interconnects, coupling capacitance, and things like that. Grids repeat specified number of tracks by circular mapping, and interacting range is usually defined as the sum of height of NMOS and PMOS. This is because we usually stack the NMOS and PMOS iteratively, but it depends on designers. Here are two examples of grade between M2 and M3, and even layers for horizontal routings and odd layers for vertical routings are common usage of meta layers. And M3 is placed on the edge of the purple colored box. You can see this? Yeah. As X increases 1, and since two grids have different spacing, and M3s are placed on different actual points, even if we do routes on the identical abstract coordinates. 8 tracks of horizontal layers are iterated with integer coordinates, and usually the horizontal spacing is defined as the contact poly pitch. Let's wrap up again here. First, LAYGO2 operates in Python, and users define the placement and routings by coding, and then LAYGO2 extracts the output as the way you want. To assure process portability, LAYGO2 uses templates and grids, and the instances are placed by following relative positional information. Grid conversion functions in LAYGO2 helps to convert physical coordinates into integer and vice versa. And then here is one thing I want to declare. It is the fact that LAYGO2 is the framework for design automation, but those frameworks are helpers to design ICs. So I think the focus should be on circuit design, not the automation itself. So I'd like to recommend the global usage of specified grids of technologies rather than generating too many flexible grids. The last part of mine is discovering LAYGO2. There are 3 packages in LAYGO2. Object package manages the entire elements in your layout design, and interface package is used when you try to output the result of your design into various formats. Object package has 4 modules. Physical module describes the physical objects in your layout, such as rectangles, pins, vias, or whatever. And then the grid module for managing integer and physical coordinates. And then template module to create template transistors and manage the template library. And lastly, the database module to manage the designs and libraries that LAYGO2 generates. Interface package now supports 4 kinds of output formats. Among these, YAML format contains the information about cells in libraries for hierarchical usage of generated instances. And also, you can add modules to this package for another toolchains. Object package contains information about every single element in your layout, rectangles, pins, or size, or locations. Yeah. First, physical module is about physically generated objects in design such as rectangles, and virtual instance. Virtual instance is the class for managing the group of instances together in LAYGO 2. Here is the example code, and the virtual instance name of inst1 includes the 3 rectangles and 2 pins. The final layout should be like the figure on the right side of this slide. The designers can control the parameters such as XY, shape, and pitch. And the information about inst1 is like below. We need some time to look at. Okay. Next is for grid module, and this is used for conversion of physical and integer coordinates, and calls the classes in physical module when we route, place, or create pins. LAYGO2 utilizes abstract coordinates, and so this module is independent of process and the architecture of transistors. Template module basically manages basic or user-defined templates. If you see this code, basic transistor model in LAYGO2 is defined as the virtual, or defined as the virtual instance class. Okay, more code here, and I think you are more familiar with codes, so I'd like to give you some time to look at, and please ask me anytime. Yeah, I'll wait for a while.
This was quite fast. So maybe like later on, Taeho, are we gonna have like some examples where all these, like some of the topics that you mentioned will be also seen? What did you plan? Sorry.
Actually, for the users, those modules are just
So this is basically the LAYGO, like in the background, basically, let's say, that enables functioning as you already kind of presented. Is that so?
yes, but I think is not that hard to understand if you look at the whole entire code in GitHub. Yeah, so I just want to explain briefly, because it can be really long if I try to explain the whole sentences, the whole lines of the code. So I'd like to briefly mention what the packages are in LAYGO2 and what the modules are in each package.
Okay.
Yeah. So yeah.
Yeah. Let's continue. I don't have any other questions. Thanks.
And yeah. The last module or object package is database that manages designs and libraries. Design class contains the entire information of whole objects in layout, such as instance, and designs belongs to library. This class is hierarchical. Since this is the dictionary format, you can access the elements in layout, in library or design via keys and values. Interface package exports your nice designs into various output formats such as GDS, YAML, and ticker. Yeah. If you run the code, the generated scale.py is like this figure. Internal handling functions are also predefined in LAYGO2, and the final layout views are created in the specified library and with the name. Those three packages in LAYGO2 have their own powerful roles, and the entire code is now online. So you guys will get more ideas by looking at those code. And this is end of mine, and Youngmin will present the generation examples of LAYGO2. And thanks for your attention. We need, yeah, if you have some questions, feel free to ask me. Or you can ask me after the presentation. Okay.
Hello, my name is Youngmin Oh from Hanyang University in Korea, and I'm going to present to you guys about how to use LAYGO2. And I'm going to talk about some useful concepts for using LAYGO2 and layout generation practice with LAYGO2 from inverter and deep flip-flop. First, I'm going to talk you guys about some useful concepts while using LAYGO2. And there are two useful concepts for represents the location of the object. First one is the pointer, that is properties which are connected to major coordinate values of object. It indicates 9 points of the object. As you can see, there is 3 on top, 3 on bottom, and left, center, and right. And second one is called B box, which is bounding box. It is property which contains the bottom left and top right of the object. It returns 2 by 2 matrix of bottom left and top right of the object, so you can easily know the size of object and use for place and routing. And to use instance for layout generation, we use generate methods that returns the instance generated from a template. We use this method with some parameters like name, transform the transformation attributes of the object to be generated, pitch, param, shape, which are optional. Pitch is the pitch of the object to be generated. Param is dictionary having the object attributes and shape of the object to be generated. To place the generated instance from template, we use place methods that place generated instance on a predefined grid. We use this method with 3 parameters: inst, grid, that grid to place instance, and mn coordinates, which is abstract coordinates value to place the instance. Place method always use this bottom left point of the generated instance when they place. And we generate MOSFET instance with various input parameters like the track sub to generate different kinds of MOSFET instance. We can generate core MOSFET with dummy, boundary, and global boundary, which can locate it in left side of core or the right side of the core. And for the core MOSFET, there are 2 parameters. First one is tie, which decide whether to connect core MOSFET to power layer like ground or VDD. And track swap decide which track to use for source or drain. And for routing on the abstract coordinate, we can use 3 methods. First one is BIA that generates a BIA on grid. As you can see on this example, we can generate we generate three BIAs on these three coordinates using this BIA function. And second one is route method, which is wire routing function generates rect object. There are three parameters we can use with MN coordinate containing two or more MN coordinates being connected, and direction via tag, which are optional. Direction decides the direction of path, which is vertical or horizontal. The default value is defined by the kind of metal layer. And via tag is a list of switches indicating whether to place via or via on junctions. As you can see, these four coordinates are being connected with three vias. When we use known, there is no via generated on this coordinate. And another one is route via track, which is advanced wire routing function that generates routing wires attached to a reference track. And it needs one more parameters that called track, that is a list containing coordinates, values, and direction of a track. Vertical track has V, non format, while horizontal track has non, V format. V means the coordinates of track. As you can see with this example, I put this track, horizontal track on this one, and these four coordinates are all attached to this reference track. Okay. And for pin information, we use two methods. First one is pin that generates pin. And there are some parameters we can use with, and with this example, we can generate pin with pin method. And for return pin dictionary of object, we use pins method, and it is important because we usually route between two pins. And now we are ready to create layouts with LAYGO2. Let's start with the simplest one, a CMOS inverter. And before we start layout generation, we have to import some modules. We import LAYGO2 module and extra module needed for layout generation. And this LAYGO2 tag contain technology-dependent templates and grids that we have to draw before the layout generation. And to start layout generation, we define design parameters for finger of mouse and type of circuit. Here we define parameters as lists to generate multiple cells at once. And second, we have to load templates to a template library object, which contains MOSFET and tab. And also, we have to load grids to a grid library object, which can use for placement and routing. And then we create a design hierarchy. The first one is the library to contain the generated layout, and then the name of layout we will generate. And we use design class to implement the design management function, and then append the generated design to the library. And in this inverter code, we use for loops for multiple cell generation. And for the layout generation, we have to create instance we will use. And we generate the MOS and PMOS instance from a template with these MOS parameters. And for PMOS, we generated believed to x-axis, which is transform called MX. And to place the generated instance, we use place method based on this placement grid called PG. And see the placement commands that utilize MN abstract coordinates. And you can see we place this MOS on the 0, 0, and PMOS of the top left of MOS. And as I said before, place method always use this top left, bottom left of instance, so we have to plus this PMOS height more. And then we have to create and place wires between two instances. For inverter input, we have to route between these two gates. And for output, we have to route these between these two drains. To avoid overlap between two metals, we use route via track for the input of inverter, and we just use route for output routing for inverter. As you can see, for input, there is a reference track, and each gate is attached to this track. And we route wires using pin coordinates, as you can see. And then we create pins based on bounding box of object. Each object is rect object, as I declared when we route. And to see layout, you have to export physical database in various output formats. Because each tool supports different format of file, example tickle file for magic and script file for cadence. So we have to export in various output formats. And you can see we generated tickle file for magic. And we export to a template database file that stores the template information in a YAML file containing size, pin position, parameters. It is optional because this YAML file is used for hierarchical layout generation, which means this generated inverter becomes a template when we use in upper level of layout. And then let's make a deep flip-flop with LAYGO2. There is just one difference from inverter generation, because the difference is that we just import inverter template instead of MOS template. So we load template in logic generated templates, which is format of YAML, which includes information of size, pin we generated previously. So we use inverter templates we generated previously for the flip-flop. And with the same flow of inverter generation and some useful method I have talked, you can make this layout of the flip-flop easily. Now you can make any layout with LAYGO2. Thank you for listening.
Okay. Hello, everyone. I'm Seonghyun, last presenter of today, and I'm from Gifted Chips Labs in Hanyang University, and I'm going to present how to set up LAYGO2 for new process at the last of today. Here is my agenda. We will start from primitive templates and grid libraries. And next, we will take a look at how to set a LAYGO2 for a new technology, and which is followed by how to convert the primitive cell libraries learned in first chapter. And lastly, we will walk through summary. Before we dive into the first chapter, many of the features to introduce in this section has been implemented for Virtuoso, not yet for Magic. But, I'll explain more specifically. Oh, sorry. Sorry. Yes. I explain more specifically. It will be treated to convert the created primitive cell to YAML files, but it's still under development for Magic. So that's why you should use other layout tools or generate YAML files by your hands. So nevertheless, these concepts is very, very important in LAYGO2. That's why I'll introduce them to you. And one more thing. This course is aimed at technology developers who should sell LAYGO2 for a new process like Skywater 130. But I think it's more also helpful for users who create layouts such as inverter or the flip-flops. Then first, what are the primitive libraries in LAYGO2 are, and how to set a LAYGO2 for a new process. If you understand these two things at the end of presentation, then I think you master of this course. Now, let's start with the primitive templates and grid libraries. This session is most important if you want to create layout in LAYGO2. In the previous Youngmin's presentation, we learned that we can generate layouts by using predefined templates and grids, right? Right. Then let's take a look at the inverter example once again. To generate layouts, we should load MOS and PMOS templates and place them on the placement grid as instance. And we complete the inverter layouts by using routing, right? Now we have a question. Where did MOS and PMOS templates come from? What about routing grids? From now on, I give you the answer about these things. MOS and PMOS are virtual instances, which are generated by combining primitive templates and grid cells from YAML file. Do you remember we load the inverter templates from YAML file? Yes. It's the same principle, but only one difference is primitive cell libraries manually run by the designer's for process before layout automate generation through LAYGO2. Can you see this image on the screen? We can classify the primitive cell into 4 categories like this. And you name the primitive cell libraries whatever you want, but we usually label TechName plus micro templates dense. First Skywater 130, the name becomes Skywater 130 micro templates dense. Now we will take a look at for each category. First one is placement grid. It defines the grid resolution to place devices. For this, boundary layer is used. And our template, which generated by us, should have the multiple size of the placement grid. And the second is routing grid. It defines the grid resolution to route the wires and place vias such as spacing, width, and coordinates. is implemented by the boundary layer and metal layers and via instances. There is a naming rule to extract the grid layout and template layout as YAML file, which has the order of routes, number of methods, and type. Here is the example. You can see two metal like M1 and M2 and boundary layers and via instances cross-section two metal wires, right? And you can design basic grids for Method 1 and Method 2 like this, and name it routes M1 and M1 M2 basic. Furthermore, you can design M1 and M2 grids for MMOS, PMOS, and even for CMOS. In this case, what can you name the grids for CMOS? Here is the hint. Right, route M1, M2 CMOS, or whatever you want is fine. This is just for example. Next is the via templates. It was placed on the cross sections of route metal wires. Usually, it's designed to have minimum width, but it's not necessary. As I said before, primitive grids and templates are created manually. That's why you can design diverse via templates. Last is the device template, which are very important. They are about the devices placed on the placement grid. There are two essential layers. One is boundary layers to specify the boundaries of devices, and the other one is pin layers. And LAYGO2 provides a generate function which creates the desired MOS or tab instances by simply adjusting the parameters. If you check this function, please just click the click button. And anyway, basically, defining device templates are up to you. But if you want to use this generate function, you should follow the define rules. The devices are divided into three parts to capture our boundary design rules. And first of the define rule is row boundary, which is placed on the left or right edges of device templates. A second one is core cell, which is kind of it have meanings what kind of these devices it is. I mean, you can know this core cell, then you can know this is transistor will NF equals 2, or this is tap cells, or this system is just like that. And last one is local boundary, is placed between core devices. I think space cell is good example. Now the naming rule is as follows. The device type like MOS for fast or PMOS fast, it comes first, and which is followed by where does it belong among the three cells. These concepts show the advantage of when adopting the layout automation in analog piano. In the digital piano, if you write the code based on the description logic, you can simply finish the place and routing. Actually, I know this is also quite difficult, but I believe you guys know what I'm saying. Anyway, that's why layout customization, I mean changing device types for long channel or short channel, or adjusting thickness of metal wires, is impossible in digital piano. But everything is possible if you use LAYGO2. You know, all parameters like technology, layer, device types, or something like that can be adjusted diversely in analog P&L. Let's say the design meta grids. Let's say you design meta grids. You can make thinner make better version or thick better version. This is really big advantage. And as you have seen so far, constructive primitive cell libraries are up to designer, right? Right. But this is the moment to remember why layout automation is needed. What do you think? Why design automation is needed? Yeah, I think there are many reasons, but I think we can organize one sentence. Is to improve reusability. I mean, primitive libraries should reflect this purpose. And next is second chapter. I talk about preparation to set up LAYGO2 for new technology like Skywater 130, Samsung 14 nanometer like that. I want to tell you once again, the procedures for MOSAIC are under development. Before we start technology setup, some pre-figures are required. First, Bag2 and LAYGO2 and 1 should be installed. Relate to MOSAIC setup, the connection between LAYGO1 and MOSAIC are currently not supported. And the PDK and layout tools should be also set. And there are total 6 files for setup and it's divided 4 categories. I'll explain step by step. First is configure file, which has YAML file. When you convert the handcrafted primitive libraries to YAML file, then this file is needed. It contains the technology specification. This is a real example. You can see all layer information like this, and the name of technology, and resolution. And then if you finish the process just before, then YAML file is generated. Do you remember 4 types of primitive cells? There are placement grids, via templates, and like that. Anyway, in this file, they are classified into two grids and templates. Here is an example. Each cell has the information about properties like unit size or extension or layer. If you want to check detail, then just click this button. And next, 3 Python files are used to define LAYGO2 database and functions from YAML files. Basically, 2 files above contain load templates and load grid functions, but you can add more functions into them if you need. And if you finish writing generated code, then you need to generate layout files in the layout tools or export them to script, right? Yeah. Then the last file, layer map file, is used for them. Just like the name, it has layer mapping information to process PDK. PDK, layer name, layer purpose, and stream number like that. But it's not needed for MOSAIC setup. This is example, and usually this file is provided in process PDK. But if you want to make this file on yourself, then just make it according to its format. And this is today's last chapter. As I said before, the YAML should be created in other ways for MOSAIC so far. Here are 4 steps to convert primitive templates and grid libraries to YAML files. First, you should draw primitive steps and write the config file. And then we should remove the back to reflect the latest version layout. After that, you generate 2 templates and grid YAML files by using LAYGO2. Configure file is used for this step. Lastly, you should change 2 YAML files to 1 YAML file for LAYGO2 format. The format converter for this has been currently provided. It's very simple because if you enter the proper input parameter, then it's done. And there are 3 key methods of the grid layout generator class in LAYGO2 for conversion. We can construct template and grid database from layout through construct template and grid method. And then we can export them by using 2 methods. Export YAML method. And it shows why the naming rules for grids are important. To make grids and templates YAML file, LAYGO2 distinguishes between them by checking the name, route, and placement. A cell is classified as the routing grid if the first word of its name is route. And this format generator is written by Python, and which changes the technology parameter of LAYGO2 to suit LAYGO2. If you click the buttons, then you can see the example I just explained. Both codes can be used immediately if you adjust the input parameter for your situation, but it's possible for Virtuoso right now. And unfortunately, it's time to conclude our presentation in summary. Let's take a look again at if we have achieved our today's goal. First, we learned about what the primitive libraries in LAYGO2 are. They should be drawn and named according to naming rules by user, right? And next, we can check what is needed, apply LAYGO2 to new process like Skywater 130. We also found out YAML file is created in this process. And these features are still being set for MOSAIC, and it's very important. I think it's enough for you to use LAYGO2 if you follow today's presentation. But actually, I forgot one important thing while explaining this setup process today. Do you know what it is? Yes. I think we are basically circuit designer, but we call ourselves layout designer because we came together to develop layout automation, right? So the one thing I missed is that we have to familiar with design rules before starting layout generation. I mean, no matter how great a tool is generated, what if it's not created to fit the design rules? Then I think no meaning. So I think that's why I want to emphasize on the importance of understanding design rules. And I think we'd better stop here. And this is end of bootcamp user guide for LAYGO2. I hope LAYGO2 will great help to the open source community. And thank you for listening for a long time and have a nice day. Thank you.
Okay, great, great. Thank you a lot. Can I start? I mean, I'm sure that people have a lot of. I mean, in the audience have some questions. So my first question will be maybe for Seonghyun. How long does it take to actually prepare the technology information, such that you can create with LAYGO2 DRC like correct layouts? I will repeat my question. So because we were talking, like the main problem usually with the generator approach is the technology information that, because of the NDA, cannot be shared from one person to another, or from one like institute or company to another. So my question for you is, how long does it take? Do you know? If you did not do it, maybe somebody else that you know did it. How long does it take to clean this technology information, to make it correct, such that once you generate your instances, it is DRC clean? Thank you.
Actually, it depends on the technology stack because it requires a high level of understanding of design rule of each process. So if you're about to create a template for really high end, such as 7 nanometer, it takes about maybe about a month, or a month for me actually, but a week for another exports. So it really depends on the designer. Yeah.
Okay. So do you, for instance, have certain strategy when you are kind of cleaning these like data? Have you noticed some correlation, for instance, between the resolution and design rules that are in design rule manual? How do you approach basically this problem? Because this is the biggest one. When somebody wants to, for instance, okay, use Skywater, that's great. But if somebody wants to use another technology, like the new one that Google announced, if you don't clean it, somebody else will have to. So what are usually the steps that you take? How do you, basically, how do you do it?
Actually, for me, I decide the resolution as a CPP, and for the structure of transistors, I usually try to see the document and I run DRC and check where the errors come up, and for the basic transistors, I try to refer my PI's structure. I mean, I'm not such an expert like my professor Jadok, so my reference is his layout actually.
Okay, thank you. Thank you, Taeho. I don't have any more questions, so maybe audience would like to say or ask something.
To microphone.
I,
So thank you so much for the presentation. It was amazing. There is a lot of work in the PPT. So my question is, what do you recommend to a designer first steps?
First steps.
Follows the inverter tutorial or anything else?
For setup or the
first design.
usage? For setup, I think you need to see the document about design rule, and for the usage, you need to it better looking the simple generator such as inverter. Yeah.
Yeah. Oh, did you use LAYGO2 for tape outs or something like that?
Yes.
How long it takes you to make a
Code.
the design or?
I wrote down a code in 40 nanometer and applied my generator to 7 nanometer. So it took about 6 months for the entire design. And yeah, but actually it depends on the quality and size of design.
Right. Yeah.
If you just want to tape out some small chip, and it will not take so long. Yeah.
Thank you.
Any additional questions?
I have one. Can you hear me?
Yes, please go
Okay.
ahead.
I did not go to the because it's all here. What do you think are the pros and cons of grid design? Do you think there are limitations?
Grid design. Yeah, there are some pros and cons actually, and I think it is more easy to design and it looks more pretty. I mean, yeah, and yeah, and for the global usage, if we do not use the grid and the individual designers just draw layouts with their own recipes. But if you use grid, the layouts are well organized, so it is easy to debug. And for the cons, I think it is hard to optimize the performance of the layout. Yeah, because the width is actually already decided. Yeah, so if you want to optimize your layout design, you need to do that with your own mouse. Yeah.
Taeho, I have a question that popped up. Sorry. So did you, for instance, check when, so, we're talking about generators that are technology agnostic, okay?
Mhm.
And I'm just curious if you have, migrated your generator from one technology to another.
Yeah.
And of course, if you have done it, how much time was it necessary to kind of redesign to hit the specs again?
Ideally, it should not be take so long, but because LAYGO2 supports parameter-based design, but there are many non-idealities in LAYGO, so it you need to, yeah, there are some trial and errors. So I think it also depends on the designer. Yeah, so sorry for my answer, but
I understand. It also
Yeah.
depends on many circumstances, whether you're new to the technology that you're kind of migrating to, etc. Okay,
yes,
I was just curious, because this is a unique opportunity to actually ask about the questions and general, like related to the philosophy that has been advertised as technology agnostic, portable, reusable. So that was the reason for my question, how actually reusable that is. So you're working on your PhD, and
yes.
definitely you're gonna have like a bunch of tape outs along your research line.
Yeah.
So how much do you reuse your own script, or is it faster for you to write from the scratch?
Um, 2 or 3 technologies of each generator. I mean, yeah, I designed the CML driver generator, and it was applied to 3 technologies without any modification. And for another generator, it is now currently used for many tape outs in my lab, even if I am not the designer. Yeah, it is easy to run and generate. Yeah.
Okay, cool. What kind of block is that?
That's a custom scan generator, which means the cascaded data shifter.
Yeah. Okay. Thank you. Thank you. I have no more questions for now. Please. We have a unique opportunity to actually ask people who tape out, in generator methodology more than once, what is their experience?
Can you ask me again?
No, I was just stating that it was not a question. I said we have a unique opportunity to ask actually some tricky questions, people who taped out more than once, in this methodology.
And
yeah.
There will be more questions about me. Yeah.
Yeah. Marco with C, do you maybe have some question for Taeho? Okay.
Thank you for the presentation because it was very interesting. And no, I don't have any further question. Maybe something about the exporting format. I saw that so is it also possible to export it in open access format? The layout?
Sorry, but please.
It's possible to generate the layout in open access format.
In open access format.
Okay, maybe not yet. Yeah. Okay, I understand.
Can you please ask me again? I'm not good at.
I mean, it's a kind of a database that contains complete information about the layout. Normally, it ends with a .oa, the file format. That's.
I think it's the one after the layout output of this also, the OA, right?
Mm-hmm.
I think that's what he's asking.
Okay, maybe I will. We will maybe talk offline. Then I will ask you better this information.
Okay, sorry.
No. Hey, thank you all for this wonderful presentation. So I have a question for Korean team. How should we proceed with with the onboarding? So let me maybe stop the recording and